A very warm greetings to all. My name is S.M. Anas, and I'm a research scholar at the Department of Civil Engineering, Jamia Millia Islamia, a central university in India. Today I'm here to present my research work. The topic of my research work is role of reinforcement, layout orientation, and spacing on performance enhancement of square reinforced concrete slab under drop load impact. This is my outline of the presentation. First, I will discuss introduction. In introduction, background and objectives will be briefly discussed, then methodology, research significance, then modeling of impact load test setup, then results and discussion, conclusions, and then finally references. Let's begin with introduction section. Impulsive loading has many facets, of which impact is the one, where structure impact is a collision between a striking object and a target structure. Reinforced concrete slabs are are having low lateral stiffness and their thickness is governed by the limit state of serviceability deflection criterion. More often, they are singly reinforced with much less reinforcement than their limiting percentage of steel, irrespective of their use in interior or exterior portions of a building. In general, concrete floors of a building quite often suffer from damage caused by the impact of falling rigid objects, explosion induced flying debris, and vehicle accidents. Collapsing load of a floor under gravity may develop a large transient dynamic load on the lower slab of the story. Slab damage under impact loading lose their in-plane strength, which alters the load carrying mechanism, leading to major damage to the structure under seismic loadings. Under such conditions, there are typically two failure modes which can be observed. First one is local failure in terms of concrete scabbing, spalling, reinforcement, yielding, punching. Another one is the major failure. And major failure means like total collapse or rupturing of the reinforcement. Objectives of my study in the present work, it has been investigated that how best the impact performance of the slab can be improved by changing the layout of the reinforcement from 9180 to 45 135. Other one is by reducing the spacing of the reinforcement from 100 to 50 mm, and third one is substituting welded wire steel mesh in lieu of conventional steel rebar mesh. For this purpose, the authors have developed a three-dimensional numerical model slab of a square slab 1000 mm by 1000 mm by 75 mm with 9180 reinforcement layout, which was tested by Sadre et al. In 2019 under drop load impact. The model is validated and the impact on the slab at its center is simulated in Abacus software with explicit module considering concrete damage plasticity model for concrete and Johnson-Cook plasticity damage model for steel. The model is subjected to a 105 kg cylindroconical impact mass having 40 mm flat nose diameter from a height of 2500 mm. Methodology used in this research work is as follows. Different approaches for investigating the response of reinforced concrete slabs under different impact loading conditions draw interest from many researchers. The most common numerical technique is the finite element modeling or finite element method, which is employed by a number of researchers in the current literature to analyze structures or structure element under different dynamic loadings, such as those induced by explosion, impact, wind, or earthquake. Therefore, FEM investigations performed by the researchers are presented here. Significance of this research work. In general, resilience is a latent requirement of the structure against possible extreme loadings, such as impact blasts or earthquake, for safety and longevity against damage. Therefore, it necessitates to assess the response of the structure or structure component under such loadings to improve structure design philosophy. Understanding of the structure response subjected to impact loading is still in its infancy. Nonetheless, development in this area is spurred by a wide range of engineering applications such as vehicular collisions with structures, aircraft crash loading on structures, the impact of projectiles, and the impact of falling boulder or rock during landslides, landslips, etc. So this is basically this figure shows the a three-dimensional model of impact load test setup, which was originally which was experimentally also developed by Sadre et al. But in this study, the authors have developed a numerical model using a Vegas. So this test setup consists of steel columns, I-beams, and a slab, or singly reinforced concrete slab, and a striker or impactor. The impactor is modeled as just above the center of the slab for applying impact loading at finite element model, and the initial velocity of the impactor is given such that it drops from 2500 mm height. As a result, the impactor is impacted to slab like drop from 2500 mm height in the numerical simulations presented here. It is important to note that the dynamic analysis conducted are only for the first free drop of the weight. Hence, accumulated damage due to repeated impact loading is not considered in this study. This table shows the mechanical properties of the material, where the RC slab is basically made of normal strength concrete having a compressive strength of 30.91 megapascal, and the yield strength of the steel bars is 422 megapascal. This is the description of the reinforcement detailing in the slab. The slab is singly reinforced, and the diameter of the rebars is 8 mm in both directions, and the spacing, the center to center spacing between the two adjacent bars is 100 mm. The clear span of the slab has a clear span of 800 mm, and the supported span is 100 mm. A clear cover a clear cover of 10 mm is provided, the same as was provided in the experimental study conducted by Sadre et al. So this is the validation of the my numerical model. So for acceptable accuracy, efficient finite element size like of 20, 15, and 10 mm are tried, are considered in the Beck's software, and you can see that from this figure. Basically, we have taken two parameters. One is the displacement time plot, another one is the damage profile, for to highlight the validation of the model. So the mode of damage with punching shear, including failure of the bond between steel and surrounding concrete, and the formation of diagonal cracks, along with maximum displacement, are closely matched and are in an excellent agreement with the experimental results of Sadar et al. With 10 mm finite element size. Therefore, the authors have considered 10 mm element size based on the mesh sensitivity analysis conducted in the analysis. Coming to the results and discussion, basically the a total of five slabs have been modeled and considered in this study. First slab is having a reinforcement layout of 9180, and this is the control slab. The second slab, in the second slab, the reinforcement layout is changed from 90 to 180 to 45, 135, keeping the diameter and the spacing of the bars same as was in the control model. So in the next model, that is third model, the spacing is reduced from 100 mm to 50 mm, and the reinforcement this model is having a reinforcement layout of 45 135 degree, and the diameter of the bar is also 6 mm. So here you can see in model first and second, the diameter of the bar is 8 mm, but in the third model, the diameter is 6 mm. Basically, the authors have tried to keep the total steel percentage same in all the models, so that all the models are having equal number of equal area of steel. In the fourth model, a welded wire mesh of 3.5 mm thickness is used at a spacing of 25 mm, and the orientation of the welded wire mesh is 90-180 degree. In the last model, that is fifth model, the orientation is changed from 90 to 180 to 45 135, keeping the thickness and the spacing the same as in the fourth model. So this is basically the vertical displacement profile of these five slabs. In the case of control model, you can see that the control model experiences a total displacement of 27.31, whereas in the second model, by changing the layout from 90 180 to 45 135, the displacement is reduced from 27 to 3.1 mm to 25.10. That is, the percentage reduction is 8%. In the third model, again the displacement is further reduced, but the reduction is very marginal. It is reduced from 25.10 to 24.10. And similarly, the displacement is also reduced with the welded wire mesh. But however, the you can see that the reduction in the displacement is not very much significant by changing the either by changing the spacing or by changing the layout of the reinforcement. So basically, in case of the control model where the layout of the reinforcing steel bar with 100 mm spacing is such that the impactor of 40 mm diameter strikes the concrete between the adjacent bars. That is, impact load is indirectly transferred to the reinforcing bars through concrete, and therefore the rebars not effectively offer the double resistance to the applied load. The concrete of this controlled slab goes downward with a peak displacement of 27.30 mm at the impacted is that is at the point of impact. Now coming to the damage profiles, computed. This is basically the computed damage profiles on the bottom tension phase of the slab. So you can see in the control model, diagonal cracks, very fine diagonal cracks can be seen. In the next model, diagonal cracks and the scabbing of concrete can be seen, but the severity is much lesser as compared to the control model. Then by further reducing the spacing from 100 mm to 50 mm, again the severity is much reduced. But however, by replacing the steel bars with welded steel wire mesh, the severity is not much reduced, and therefore this slab and the damage to this slab is slightly higher as compared to the slab having steel rebars. Steel rebars. So change layout orientation of the steel bars from 90 to 180, 90 180 to 45 135 in this model alters the mode of punching dominance to flexor with crushing of the concrete at the point of impact with a decreased crushing depth from full depth in reference slab or control model to almost one-fourth of the slab thickness from the top. Slab S5, S45, 135, 650 with the same steel percentage as that of the as that of slab S45, 135, 800, but having a reduced spacing of bars from 100 to 50 mm center to center and diameter from 8 to 6 mm displays improved impact resistance in terms of damage severity and concrete scabbing on the bottom tension phase of the slab. Finally, coming to the conclusions. So, the main conclusions from this study are as follows. The response of the reinforced concrete slab with conventional 90-180 reinforcement orientation is basically governed by a dominating mode of punching shear under low velocity impact loading. The slab with same percentage of steel reinforcement and diameter of reinforcing bars with 45 135 configuration layout changes its failure mode from punching shear to flexor but with scabbing on the rear face. This shows that layout orientation significantly influences the response of the slab with regards to failure mode and damage. However, reduction in maximum central displacement remains less significant under the impact. Reducing the diameter of the reinforcing bar from 8 to 6 mm with 50 mm spacing center to center in slab S45 135 650 shows improved impact resistance in terms of reduced damage severity and scabbing, but not with respect to maximum displacement. Replacing the conventional steel bars with welded mesh steel wire of equivalent area increases the damage severity, resulting in more scabbing and depth of diagonal cracks with almost similar displacement compared to the S45 135 650. Finally, it has been observed that rebar layout orientation uh, with the same tension steel ratio improves the damage by reducing its severity from extensive to less moderate level without affecting the slab displacement under the low velocity impact. In this research work, we have a total number of references used is around 60. And thank you for your kind attention. Uh, Thank you very much for your kind attention.